All right, we're going to talk about the first topic in our unit on integration. Before we start talking about integration, we have to understand antiderivatives. So we'll start with antiderivatives and build our way towards indefinite integrals, and then we'll end this with talking about initial value problems. First thing let's introduce is a definition. Kind of a funny definition. I really don't like the notation that math people insist on using when they talk about integrals and antiderivatives. So let's just talk through it quick. A function capital F is an antiderivative of the function little f if capital F's derivative is equal to little f. I said something I'm going to write later. Big F, little f has derivative. Wait, little f is the derivative of big F. Yeah, we're gonna. Please forgive me that brief hiccup. Okay, so what does this actually mean? Let's just write something out. It has to do with my problem is everything is always f of x. The expression you're going to be given is called f of x. And it's going to be written as f of x in your textbook and in your homework problems. And so they try and relate the notation to that. And I sometimes think it clouds the idea. So let's just write that expression over here. Oh no, don't zoom in. Sorry. Oh, fit the width nicely here. Okay, so big F of x, the derivative of big F of x is little f. Okay, and that is related to big capital F over here. Okay, so look at the bottom direction here. If I go from left to right, big F has derivative of little f. And then we call little f, or the derivative, little f has antiderivative of big F. And really all we're saying is we're just thinking in reverse. What you're going to be doing, what we'll be doing is we'll be given some function f of x, and we want to find its informal here, its parent that has little f of x as its derivative. That's what antidifferentiation is basically you're given the derivative and then you're looking to find the quote parent function that has that of whose derivative you're examining. And unfortunately that's how the notation has to look to express that idea formally, but hopefully that puts a little more intuition on it. Let's just plow in recklessly forward and try some examples. So find an antiderivative for the given function. F of x is equal to 3x raised to the second power. So we want to think about this and say, okay, what has the derivative 3x to the second power? Well, the power rule is drop down the exponent and subtract 1, looking at 3 being 1 bigger than the exponent of 2. And I want you to take a minute and to actually check this. Big F of x, and that's, big F of x. We're just going to stick with their notation for just a second. Big F of x, our antiderivative, the parent function, capital being the parent of little. What has derivative 3x squared? Well, x raised to the third power. And sure enough, power rule, drop down that 3, x to the third prime. To check this, we could drop down that 3 and then subtract 1 to get 3x2. We see that it works. Okay, so we're given the derivative and we're looking for the parent, the antiderivative, if you will. So what has derivative 1 over x? ln. The natural log has derivative ln of x. ln of x differentiated is equal to 1 over x. It checks. Lastly, what has derivative, well, not lastly, another example, what has derivative cosine? Sine does. F of x, big F of x, the parent, sine of x. And sure enough, sine of x, take the derivative of it, is cosine of x. What is derivative e to the x? Well, that's my favorite one. E to the x has derivative of e to the x, so much so that, yeah, let's check it. E to the x is equal to, and look at what we're actually writing. We're writing capital F of x prime, the derivative of our big guy, is equal to our little guy, e to the x. But don't get hung up on notation. Focus on the idea that you're given the derivative and you're asked to find the parent function. So I have, why did I say an in the lower corner? Why did I say an antiderivative? Well, antiderivatives are not unique. So let's think if we can find 3 different derivatives of 3x squared. Well, the first one, let's just work with the one that we came up with. X to the third. Sure enough, x to the third has derivative 3x squared. So what could be a second one? Well, I don't know how. We need to be able to take, it's got to have x to the third, because that's how you get the derivative of 3x squared when you take the derivative of it. So what can we do that is going to not add any new expression to the derivative? Well, here we're going to exploit the fact that the derivative of a constant is 0. So we can just tack on 2 for any old number if you like. And sure enough, to check x to the third power plus 2, take the derivative of it. And again, yeah, it's going to be 3x squared from the x expression plus 0 for the 2 expression. And we've done it. That expression, 3x x to the third power plus 2, has derivative 3x squared. So x to the third power plus 2 is an antiderivative of 3x squared. And so hopefully during that explanation, you're like, oh, well, you could do this with any constant. Sure enough, we can. X to the third minus pi divided by e. You could get crazy. It doesn't matter. Pi over e is just a number. Take the derivative of that expression, x to the third minus pi over e, gives us 3x squared plus 0. Sure enough, they all check. So this was meant to introduce the idea that antiderivatives are not unique at all. There are lots of them. In fact, there are an infinite number of them, because you could tack any number on through addition and subtraction, which is what the next slide says. Antiderivatives are not unique. In the last problem, we found an antiderivative for 3x squared. We came up with x to the third. There should be an end parenthesis there. In general, x to the third plus any constant c will also work. So for that reason, sometimes we refer to the general form, or sometimes this is called a family of antiderivatives. There's the parent analogy again. An antiderivative has, oh my goodness, I'm botching my words here, but yeah, you can add on c. The notation gets complicated. Let's move on. Okay, so that's what antiderivatives are. Well, what's an integral? We're going to start with indefinite integrals. We'll pause this here and continue.